tapping over here.
All right, everybody ready? Sorry, no.
What?
I thought I scared you.
No.
It scared me. Gosh. Still going. Still going. Could you hear it back there still even? Yeah, it's amazing, isn't it? Like how long it goes. And I love the beginning when it's like almost spinning around, right? It's like whoa, whoa, whoa. And then that frequency, oh, it's just glorious to hear bells.
That reminds me of this one video I saw of this guy. He had like a metal plate and like sand on it, and he like banged the side of it, and all the sand just like fell into place of a function.
Yeah, I've seen that. Yeah, it's amazing.
Wow.
Yeah, I kind of want one of those. Like, I bet Dr. Gray could help us rig one up. That would be so cool. And it's those sonic, I forget what they're called. There's some kind of plate. Let's see. Hey, friends. Welcome back. Somebody asked me, who was it that asked me about when our next exam was?
Not me.
Olivia.
Definitely wasn't me.
It was Olivia. I don't want to know. It'll probably be in like 2 to 3 weeks, something like that. It's like, there's only 2 exams, and the hard part, if you had my classes before, which almost everybody has, the exams are easy. And, you know, you gotta know some basics, but all the real suffering comes in your homework. When you have lots of time to suffer, not when you're under duress. Fuck that. All right, so the homework assignment is up. Make note that it's problem 18 with all the parts, not 17. So you don't work things you don't need to work. All right, so let's see, where were we? Differentiability. I guess we just talked about R. Isn't that right? We talked about real differentiation, but we didn't get into the complex yet. So this is going to be some things that don't seem terribly shocking. Because the definition of the derivative is the same, it just means something a little bit different. So I have this function f, complex valued. That's a subset of the complex plane. This is its domain. Let's keep saying that in different ways over and over throughout the semester. So we define the derivative of f at z naught to be f prime at z naught equals limit. I'm going to do this 2 different ways. First, I'm going to do it like we did with the real derivative. So h goes to 0, f of z plus h, f of z naught plus h minus f of z naught over h. A note here. H going to 0 is a complex number going to 0. So this h going to 0 here, remember that h is equal to some x plus iy. So that when we think about going to 0 in the complex plane, remember that delta neighborhood that we talked about? We're getting closer to 0 and allowing for every possible way of doing that. So we have a neighborhood shrinking to 0. And no matter what point we pick out of that, this thing is headed toward a limit, no matter how we route ourselves towards 0. I've got a problem in this problem set that's gonna let you kind of see a kind of a cool thing here, like a thing that has a derivative along every line, but not along a parabola, which is kind of wild. It's something like, it might just be a limit that exists. So, just keep in mind, that is a complex number. This is equivalent to, so here's the other one, and this one's a little bit more useful, that we're gonna look at the limit as z goes to z naught. And again here, what does that mean? Here's the point z naught. We can approach in any way, from any direction, of f of z minus f of z naught. So the change in f over the change in input. If this thing exists, so simply writing that there's a quantity equal to this means that it exists. So let's just put that here though, if the limit exists. If the limit does not exist, the function is not differentiable at that point. We don't have a really beautiful interpretation of smoothness like we did with the real numbers, where we don't want to have kinks with the real numbers. But here, kinks are really hard to see because it's in 4 dimensions. I don't know what a 4-dimensional kink looks like, but we can find them. That sounds pretty weird, doesn't it? So let's get another couple of other definitions out here. Sorry, that's why I got my notes here so I don't forget and lose my mind more than I already have. All right, so if f is differentiable, in other words, that limit exists in an open disk about point z naught. We'll talk about what all this means in a minute, because this is a much stronger thing. Then f is holomorphic. Whoa. Yeah, that's a crazy awesome word. Holomorphic at z naught. Different depending on what complex analysis book you use. They'll either use the word holomorphic, which is just awesome, right? It is like anything that starts with holo is like holographic. Oh my God, everything's wild. But equivalently, we would call it analytic. That's less cool. It's yeah, agreed. In some books, or just different places. So I might slip back and forth and say analytic or holomorphic, and they mean the same thing. So look at this. This is a much stronger thing than being differentiable at a point. What we're saying here is that at the point z naught, we are differentiable, but that there is this whole open neighborhood around that, and at every point inside there, that derivative exists. So derivative exists at every point. And now I can put my z naught back. At every point in an open disk about, and I'm kind of just saying the same thing again there, so maybe you don't need to put all these words, in an open disk centered at z naught. The picture definitely helps, and putting a note that it's not just a local property, it's a neighborhood property. If, this is the word I screwed up last time, if f is analytic, so now I'm just doing it again. Analytic, aka holomorphic. Now I'll do it backwards. Holomorphic at every point in the plane, it is called entire. And there's no other word for that one. So an entire function is like that's like the pinnacle of differentiability. The derivative exists no matter where I go. It's beautiful. No problems with derivatives anywhere at all. Yes, sir?
Why does it matter if the disk is open for holomorphic?
Huh, that's a good question. Oh, because we can't do the derivative at a boundary point I think, and I think this is it. So if I had like a point, and then I said it's differentiable at every point in a closed disk around there, what if it's not differentiable? So say we're differentiable in here and not differentiable out here. I don't think we could here's why, I got it. Because differentiability requires that you can approach from every direction, and once I have a closed disk, points on that boundary now cannot be approached from a lot of directions.
Okay.
Does that make sense?
Yeah.
Yeah, I think that's exactly what it is. Good question, really good question. I had to think about that one. Any other questions so far? And we're gonna play with this a lot. And like, I see Lavina trying to translate my Sanskrit. Can I help? You think you got it? Okay. It says, I'll just read it to you. Deriv exists at every point in an open disk centered at Z naught.
Okay.
No, let me translate.
Let me try.
So once we have an analytic function, there's kind of something cool that happens. Because like checking at every point in some neighborhood, differentiability is pretty much untenable. It's not something we can easily do. So how do we discern if a function is analytic anywhere? Let alone just like differentiable, but analytic anywhere. So let's derive. I'm going to derive something. I don't do a lot of derivations in here, but let's do this one. So let's suppose that f of z equals uxy plus ivxy. Now I want to talk about that for a minute, because I feel like I've said stuff about it, but we haven't really, it might be a little confusing to see what I mean here. So let me show you for example. So example. Every complex function can be written as a real part and an imaginary part, and it just might take some work to get there. So let's say we had f of z was z squared. And we're going to replace z with x plus iy, and see what that looks like. So in other words, this is x plus iy squared. Work it through, FOIL it out. First, outer, inner, last. And then on the last, I get an I squared, so I get minus y squared. I get iy times iy.
Okay.
That's I squared, y squared, negative 1, y squared. Is that cool? Just let me know if it isn't. Cool, Cindy. Because there was this. Okay, cool. Whoa, wow. Exciting times. Minus y squared. So now I'm going to group together the real stuff, and I'm going to group together the imaginary stuff. And so this would be the u that depends on x and y, and this is the v of x, y. Right here.
Every function has to be able to do this?
Every function this can be done to every complex function. Yes. Sometimes it'll actually just be explicitly written in this form, but no matter what it is, we can always get to that place. Which actually, it does seem kind of amazing in some ways. It kind of seems like, oh, there's got to be something that doesn't work for.
Yeah, I mean, I guess all your answers have to be kind of uniform. So.
And the function, the u and the v might not be pretty.
Yeah.
So we'll leave it down. If we had that, it's probably a little more believable. So let's also suppose that the derivative exists at a point z naught. So the f prime of z naught, and we'll go to this definition here, because I think this is probably easier on your brain. Z naught plus h minus f of z naught over h. So that point z naught, we're gonna want to go to that form for what is about to happen here. I'm gonna intertwine these two things together and rewrite this limit using that form. So I need to say what z naught is going to be, and so it's going to be x naught plus I y naught. And I'm also going to write this h. Remember, this h is a complex number. That's a complex number, so we're going to say that h is equal to h x plus h y sub x h sub y I. So I'm just writing h as a complex number, because it is a complex number. I just don't know what parts are. So I got to label them. And now we can come and start seeing what this does to this limit. So with those substitutions, this is limit as, we'll just write hx plus hyi goes to 0 here. And then I've got, let's actually just take a minute and write out what this is going to take a couple steps. So that's x naught plus I y naught, that's the z naught. So that's this, plus hx plus hyi. And then I'm going to say minus f at x naught plus I y naught. And then that's all over good old h sub x plus h sub y. Give you a minute to get caught up. Following, let me know if anything needs clarification. Let me get, yeah, people writing, thinking, awesome, take that time. So in the next line, I'm just going to take this and then go to this form. So I'm going to replace each f with that, and this is going to get big. So we're going to have lim as h sub x plus h sub y I goes to 0 of f is equal to u of xy plus iv of xy. Now think, oh here, let's actually take a quick little sub-step here. This stuff can get simplified. So this is x naught plus h sub x, that's the real part, plus y naught plus h sub y, and then that's all I stuff. So just taking that and noting this is the real part of this input, and this is the imaginary part of that input. That's how the h combines with the x and the y. So let me stop to make sure that that is clear what I'm saying there. Does that sound okay? Yeah. Awesome. So now when I come here, this is the x, right? Because this is the real part, so that's going to go in for the x coordinate, and this quantity, y naught plus yi, is the y. So this is equal to, we're going to need some brackets out the Yahoo, I think, here. So we've got u of x naught plus hx, that's the x part, and then the y part is y naught plus hy. So that's just this, plus iv of x naught plus hx, y naught plus h sub y. So that's just this. This thing is now rewritten in terms of u and v. And then minus, now I'm going to write this part. And this part's a lot easier because this is just going to be u at x naught, y naught, plus iv at x naught, y naught. And that's all over hx plus hy. Yes, sir?
Is that a y or a v? Like that's a y, right? IV times x naught
Yes, this is iv
times x naught plus
x, yeah, of x naught h, x naught plus h sub x and y naught plus
Okay,
h sub
y
y.
naught.
Yes. Always happy to translate. I need to be happy about it. You good, Sydney? I know you so well. I can tell you have a question.
Oh no, I see.
Oh, cool, awesome.
Okay.
No, nice, solid. Yeah.
Excellent.
Making sense? Our next move is to rewrite this. Let's see, let me just make sure I'm going to the right. Yeah, we're gonna group together the U stuff and the V stuff. Because notice the V stuff has an I on it. The U stuff doesn't. But there will be a shared I in the bottom. So let's just rearranging h sub x plus h sub y I, shrinking to 0. And on top, now I'm going to break this apart like I said, so I'm going to have u of x naught plus h sub x, y naught plus h sub y, minus u of x naught, y naught. And then that's all over this. And now we're going to write the v stuff over here. It's going to look the same, it's just going to have v's and an I tacked on. So we're going to have v of x naught plus hx, y naught plus hy, minus v of x naught, y naught, all over this beast, and then an I. I'm going to let you get caught up because that is a lot of writing.
I always hate having a lot of subscripts because then when I start writing them over and over again, they start looking like constants and
Not
stuff.
subscripts,
No.
yes, yes.
Like, ooh.
They start crawling to the surface, yes. I dressed up today because I think we're doing our department photo, like the group photo, so I was like, oh, really?
Aww.
It's gonna be up for a while. Like the last one was taken like 10 years ago or something. So gotta look good because it's gonna be around for a while. Any questions on getting here? No? Okay. How many different ways can I approach 0 here and have this value be the same? Answer is infinitely many. We are saying this limit exists. And we know that in the complex numbers, that means that this h can approach 0 in any way, and this limit will always be this number. I will get the same answer no matter how this h approaches 0, because I've said it exists. If I didn't write that, I wouldn't know it exists, but the minute I put that equals this, it means we're good, that limit is going to be solid, no matter how h gets to 0. And we're going to look at this limit in two different approaches. So in the first approach, we're going to approach on the real line. So we're going to, one part of this computation is, what does that limit look like if we approach on the real axis? And then we're going to do it on the imaginary axis. So let's actually think about, let me come back and get rid of this. If we approach 0 on the real axis, so h approaches 0 on the real axis, that means h sub y is just 0. So this piece is gone. Yeah, does that make sense? And then the h sub x is just going to 0 on its own. Maybe from the left, maybe from the right. This is turning into like a Calc 1 thing, kind of. If you had Calc 3, it's even more of that. You probably haven't gotten to derivatives yet, is what I'm thinking. Who's in Calc 3? Did you get to derivatives yet? Oh, okay, cool. All right, so first, assume hy is equal to 0, and then hx is just going to 0. That's this approach on the real axis. So real axis approach to 0. And then let's just rewrite it. So this limit is equal to the limit as hx goes to 0. Cool. All the hy's go away. So we're just going to rewrite all this stuff with hy erased. I've got u of x naught plus hx, comma, y naught, minus u of x naught, y naught, all over hx. Starting to look actually a little more sane. Looking like some real value stuff going on here. Plus v of x naught plus hx, comma, y naught, minus v of x naught, y naught, all over h sub x. And there's an I. Somebody tell me what those are. What is that expression, that fraction for u with the limit? What is that expression for v with the limit attached? What are we finding there? What does it kind of look like? Just look at this one. What does that look like?
The derivative of u with respect to x.
So this looks like a derivative, right? We're taking one of the variables, we're bumping away from it a little bit, we're finding the difference from the output at that bumped input minus that original output. So we're just looking at the change in u. So just look here, this top here is the change in u, and this is the change in x at the bottom. So this down here is the change in x. We're just changing the x value. Y is like a constant. This is the derivative of u with respect to x, treating y as a constant. This is called the partial of u, so that's a partial derivative of u with respect to x. What is the instantaneous rate of change of u with respect to x at this point, x naught, y naught? So that's what that equals. What is this right side? What is that going to become? Somebody besides Noah, tell me.
The partial of v.
Beautiful. Because it's the same thing, right, with just v. And we've got a y tacked on. So partial of v with respect to y at x naught, y naught. Excuse me, with respect to x, sorry. At x naught, y naught times I. Okay, so I just want to point some things out because there's some crazy stuff that just happened here. This whole thing is this. You getting the point that it's this if I keep circling that much? Psychotically? Have you ever seen the movies where it's usually a woman because in the past this was shown this way, putting on lipstick and crazily, it's like crazily. That's what I'm doing right here. Crazily circling f prime of z naught. So this is f prime at z naught. There's actually a formula for it. Huh. What an odd formula. It just involves x. Derivatives with respect to x. That's interesting. Now we're going to approach vertically. So we're going to do the same computation, except this time we're going to let hx equal 0 and let hy be the thing. So now let hx equal 0 and hy approach 0. I.e. approach 0 on the imaginary axis. And crank this through. Just do the same thing. But now it's going to go a lot faster because we can just come to this and we're going to replace every hx with 0. We're going to leave the hy's in. That's going to go to 0 there. That's going to go to 0. That's going to be 0. Dead, 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 dead. So what we've got is limit as h sub yi goes to 0, because h sub x is 0 in this direction, And then we've got u of x naught y naught plus hy minus u of x naught y naught. And that's all over h sub yi. Plus, now we got the v thing here, and that's just v of x naught y naught plus h sub y minus v of x naught y naught all over h sub y I. What's up?
Times I.
Times I, thank you, Sydney. Yeah, that would have been pretty important and would have sucked if I had lost it, so thank you. Good eye. There was that original I right there, which is kind of cool because that's going to cancel with this I. Do we see that? That these two I's cancel. This I's in the bottom. We'll just deal with that in a minute. What, somebody else tell me now, what does this go to as the h sub y shrinks to 0? The displacement in the y coordinate dies out. What does that go to? No, think kind of similar to this.
The partial of u with respect to y.
Yes, yeah. So, yeah, this is the partial of u with respect to, does that make sense?
Yeah.
Yeah. That's what I'm looking for, because here we're just taking the derivative on the y value, on the y variable. So this is derivative of u with respect to y at x naught, y naught, but there's this 1 over I there, right? I'm just gonna kind of pull that guy out. This one's gonna cancel, so that's gonna be sweet. So this is plus, what? What's this guy become?
Partial of v with respect to y.
Yeah. At the point of interest. That is also this, because it doesn't matter how we approach. So now we have f prime at z naught must also be found by, you can find it by this formula. Let's summarize on the left side what we know and do a little simplification. What does 1 over I simplify to?
Negative I.
Negative I, indeed, it's negative I. So just take a look at 1 over I. How do we do that? Well, that's, you multiply by the conjugate, right? So that's 1 times negative I over I times negative I. And on top you've got negative I, and on the bottom you've got negative 1, negative I. So 1 over I is negative I. And I'm going to replace this with negative I. Heretofore and thusly.
Heretofore and thusly.
Yeah, or whatever you want. Whence, hence, so. So, f prime at z naught is computable by this formula, partial of u with respect to x at x naught y naught, plus I times the partial of v with respect to x at x naught y naught, and it also equals negative I times the partial of u with respect to y. Wait, is that right? Yes. No. Yes, with respect to y. Sorry, I'm saying and I'm not writing properly at the same time. So negative I times partial of u with respect to y plus partial of v with respect to y, x naught, y naught. Almost done. I want to compare these two things. These have to be the same complex number. So that means this, with that negative included, has to be the same as this. And this, the real part, must equal this. So in other words, the partial of u with respect to x at the point of interest must equal the partial of v with respect to y at the point of interest. And the partial of v with respect to x at the point of interest is the opposite of the partial of u with respect to y at the point of interest. Let me summarize. If a function is differentiable at a point, these two equations must hold. So let's just write that here. These are called the Cauchy-Riemann equations. Please say Cauchy as Cauchy. People say that weird ass all the Cauchy and stuff like that. That's Cauchy.
Cauchy and Riemann?
Cauchy and Riemann.
I've heard of both of those.
Yeah, they are.
Just not together.
Yeah, it's crazy. I mean, they were around at the same time. This was pretty golden era for mathematics
Cool.
and insanity
Apparently.
in mathematicians. And then it just kept going. The Cauchy-Riemann equations, which say, in short, I'm going to write it in shorthand here, if f is differentiable at a point, partial of u with respect to x is equal to partial of v with respect to y, and the partial of u with respect to y is equal to negative partial of v with respect to x at that point. Look at the flow here. If, then. If, then. I'm not saying if and only if yet.
Yet.
Not yet. If it is differentiable, then these two hold at that point. We'll get an if and only if we ask a few things about these partial derivatives. Mostly that they are continuous on a region near that point. So, let me just put up a definition here. A function f is continuously differentiable on a set G if it is differentiable, that makes sense, and the derivative is continuous. That's a D there, boy, that's a weird, I'm just gonna rewrite it. Derivative is continuous on G. That's gonna happen most of the time. You have to like walk 1 billion miles out of your way, dig up some stuff at the bottom of a quarry, really get down in there. You need like blasting materials and stuff like that to come up with something where this isn't the case. This is like always gonna be the case. This is always gonna be the case. I haven't gotten to what is the case yet. So, Cauchy-Riemann equations satisfied if and only if f is differentiable and u and v are continuously differentiable. And I should be precise here, on an open set around the point of interest. You've probably seen this before. Have you ever seen Clairaut's theorem in Calc? Did your Calc 1 teacher talk about Clairaut's theorem? About how second mixed partial, oh, this was Calc 3, isn't it? Calc 3, who's had Calc 3? Everybody in Olivia's in it. Do you remember Clairaut's theorem that's mixed partials? Like if I do partial of u with respect to x, then y, that's the same thing as the partial if I do y first then x. And that's only true if these derivatives are continuous. And you can come up with an example where this doesn't hold, but it's the same condition essentially as we see over here. That's called Clairaut's theorem. And we just take it for granted. We're just like, oh yeah, uxy is uyx, whatever. We never worry about it. Because you don't have to worry about it. So, these, my friends, are going to be your bread and butter for a long time in this class. Cauchy-Riemann equations. Let's use them. We just paid dearly to get there. So let's have fun now. Now it's fun time. So much fun. Let's prove that f of z equals z squared is entire. Its derivative exists everywhere in the complex plane. And so to do that, we first need the u and the v form of it, which we already cranked out. So that's convenient. So step one is write f in u plus iv form. We've done that, luckily. That was x squared minus y squared plus 2xy. And then I identify what's u, what's v. So here's u, here's v. And when the I doesn't come along, the I is holding the V. It's letting us know what V is. It's the thing in front of the I, or by the I. Everything but the I. So now I gotta crank out, we're gonna do a check, Cauchy-Riemann. So you need to crank out these derivatives. Partial of u with respect to x. You treat the y as a constant, so u sub x is 2x. Now I'm using that notation here. This just means, just to refresh your memory, that's partial of u with respect to x. It's just a lot less writing. And then v with respect to y is going to be what? 2x. And you could get there by doing it or by knowing that I already said this works. And so it has to be the same as u sub x. But notice that these are equal everywhere. They're literally the same expression. So no matter what x I put in, ux is equal to vy, beauty, no matter what. And then we crank out uy. What is the partial of u with respect to y? Negative 2y, beautiful. And then v with respect to x is? 2y. Remember what Cauchy-Riemann says. It says that uy equals negative vx. So let's just make that out here. Since u sub y equals negative v sub x, there's a twist that occurs right there. Since that is the case, everywhere, for all values of y, it doesn't even mention x, so x is free. Doesn't matter what x is. Everywhere in C, these conditions hold. The Cauchy-Riemann equations hold true. So CR EQs hold true everywhere. And now I know that function is differentiable everywhere. And so it is entire. And those are certainly continuous, right? Like, those are just like polynomials. They're just linear functions. So let's just make a little note. This will be something it'll just be true most of the time. These are also continuous. Everywhere. One of the great uses of the Cauchy-Riemann equations is showing something is not differentiable. And it's kind of crazy, the stuff that's not differentiable, and I want to spend some time talking about the geometry of y. Yes?
So, if the Cauchy-Riemann's hold true everywhere, is it differentiable everywhere, or do we not know?
It is differentiable everywhere. So any point at which Cauchy-Riemann equations hold true,
And, and,
and they are
and
continuous.
they're continuous, even if we don't check it from different directions.
Yeah, because the different directions has already come into play in the derivation of the Cauchy-Riemann equations.
Okay.
Yeah, we're safe. You're completely safe. Are you concerned because the Cauchy-Riemann equations were only derived using two different directions?
Yeah.
So let me address your concern. We would actually have to go through a much more deep proof to go the reverse. Like what we did was say f is differentiable, therefore doesn't matter what I approach from.
Yeah.
To show the other direction is a much more intricate thing, a much bigger proof, but it can be demonstrated. It's just like a little beyond what we probably want to do in here.
Okay.
But I will get it for you.
Cool. I'm gonna read it.
I believe you will. I will get that for you.
Okay.
Other questions before we go on? So CR equations are excellent tools for discerning non-differentiability. Or places where differentiability might fail, where they're just not equal. There's variables and stuff, but in some places they can't be equal. So let's take a look at that. I think I spelled this, no I didn't, I said discreening. So let me fix that, discerning, yeah. So let's take f of z is equal to x plus 2yi. Boy, does that look beautiful. I mean, right? That's like freaking linear almost, or something. This thing's gotta be different, and you can tell it's not gonna be from my setup here if I get my routine. But this is not differentiable. Wild, let's prove it. It's not differentiable anywhere. There's not a single point that this thing is differentiable at. Hold on to that thought, because I want to contrast that with the real numbers, where something like this is really hard to find. So this here, so we're going to check the Cauchy-Riemann. So check Cauchy-Riemann. So you do ux, how about I just let you do this? Ux, vy, uy, vx. See if you can see that this function is not differentiable anywhere. My derivative's looking okay. Yeah. We definitely have this, right, because they're both 0, but we do not have that primal one. So here, ux is not equal to vy everywhere, so f is not differentiable. We don't even have to check the continuity stuff in this direction because this is the contrapositive of if differentiable, then Cauchy-Riemann holds. This is the contrapositive. If not Cauchy-Riemann, then not differentiable. So f is not differentiable anywhere. Isn't that just blows, that has always blown my mind. That such an elegant, beautiful, simple thing is not differentiable. I think it's pretty shocking. Bless you.
Thank you.
And so the thing I want to talk about is why. Why? What is happening when we say a function is differentiable in the complex plane? Because it's pretty intense. To come up with a non-differentiable function in the real numbers, has anybody ever seen that? Who's in real analysis? Did you build a did we did that?
We did that.
Yeah, we did that. To build a non-differentiable function in the reals, you have to literally go to fractals. Here's how you build a non-differentiable function in the reals. You start off with this, and then you start putting little kinks in each side. So then you go, oh, okay, like that.
Oh,
And do you remember doing this?
we did that with triangles, right?
Yeah, it's probably, I'm kind of like hacking the process, I don't quite remember. But you go through an iterative process where every time in the process you take whatever is straight and kink it a little.
It was
What was it?
it was a like absolute value of 1 minus x or something, and then it was a triangle, and then it was 2 smaller triangles.
Oh,
And it was 4 smaller triangles.
like this.
Yeah, and then you would add 2 smaller triangles to that. I don't know how that looks.
Yeah, you gotta be careful just so that you keep functionhood, you know, but yeah, because that,
No, it's like I don't know the shape, but
Yeah.
It's like
The
a
shape that you add
triangle
before
and
they
then smaller
combine
triangles
is-
inside and smaller triangles inside. It's like
2 triangles that are half of that size.
Yeah.
oh, like that?
Yeah.
Yeah.
And then you would add that to the first.
Oh, that's it, yeah, and then add that to this,
Mhm, and then you
and
get
then
something.
do that.
Yeah.
And keep adding those together and like
Yes.
looking at the sums. Yeah, that's right. That's one way to do it for sure. And you add these together, and the resulting function ends up looking like this. It's something really fuzzy, and it's infinitely jagged. No matter where you zoom in and how far you zoom in, it's still jagged. It never looks like a line, which is what differentiable means in the reals. In the reals, something is smooth if I can zoom in on it close enough that it looks like a line. That's what differentiable means, approximately linear locally. This is never linear anywhere. But look at this, we didn't have to go far. I just freaking tacked a 2 on there. How could I alter this so that this function did become differentiable? What if I put a b there? What should be equal? 1. Yeah, so to this, now that's differentiable, but nothing else is multiple-wise. If I put any other multiple there, it's not differentiable.
Interesting.
Isn't that interesting? Even that guy, huh? Not differentiable. So what in the heck is going on?
It's a great question.
It is a great question. I hope I have a great answer.
Me too.
I do. You're right. You're right. Our book doesn't talk about this. I've only seen this discussed in one book. It's called Visual Complex Analysis. Really cool book. If you're interested in the stuff we are doing here, this is a beautiful book to pick up. Just a really beautiful book. Very intense book. So I'm going to paraphrase some of the things that are from there. But if we have f prime of z naught existing, what does that mean? Well, this thing here, let's go back. Remember the other day I was talking about it, left us off with this in the reals. So real valued stuff looked like this. We had a point, we're saying we're differentiable there. If I take an infinitesimal stroll away here, that corresponds to a predictable infinitesimal stroll away down here. If I slightly alter that, this slightly alters down here. So there's like a kind of a continuous response between these two things. This thing doesn't like just jump wildly. In the complex plane, what this means is that I'm going to take this thing here. So if I have w equals f of z, and then I take derivatives. So this becomes differential w equals f prime at some point z naught dz. This is my output change. This is my input change. So what we're saying here now in the complex numbers is that if I'm at z naught and I move just a little, now that little is infinitely many different ways. So there's my dz. If I move just a little there, what happens to the output? So take that little tiny infinitesimal vector, dz. I'm saying vector, it's just a complex number, which is pretty much like a vector, right? And then I run that through f. What comes out is this point w naught. And that's the image of z naught. So what I'm saying is this right here. This w naught has a corresponding change. I can see exactly how this vector changes by just multiplying it by the derivative. So over here, we have dw, but that dw is equal to f prime at z naught, the derivative value here, times the infinitesimal vector change over here. Now, what does this look like? This is a complex number. And I'm just multiplying this little thing, this little infinitesimal change over here by a complex number to get the corresponding change over here. Like, where am I pointing? What's its magnitude? So it's a complex number, but we know that that is equal to a magnitude, so an amplification, an amplitude, which we call the modulus, times some e to the I theta part. This is a rotation. So we have an amplification, which might be also shrinking. Amplification times a twisting. In this book, I've never seen this anywhere else, but I think it's beautiful, that being differentiable in the complex plane means your function acts like an amplitwist. Amplitwist. Your derivative locally amplifies, it magnifies, maybe shrinks or expands. It amplifies and it twists every single thing here in the same way. So this guy here gets amplified and twisted by the same amount as this one did. So it's like taking this region, and if this region is a disk, the output remains a disk, and it's just rotated. So see that big arrow there? That's going to maybe come down here, and then that little one there that looks like they're at 90 degrees, they stay at 90 degrees down here. So you get this rotation and a amplification. So let me just write that up here. A complex differentiable function acts on infinitesimals, really small things, as an amplitwist. So that is uniform scaling and rotation. At the deepest level, this is what's happening. I've got some like crazier shit I messed with, and I don't think I'm going to put up on the board. But maybe I'll write it up and just give it to you for your amusement as you see fit.
So you couldn't flip it?
Yeah, no, it cannot be a flip because that's not a rotation. That's an awesome question. So it can't take a vector and like take its conjugate or something. You can't get that kind. It has to be a smooth action. Yeah, that's a great question. So let's think, now that I think of that, is this function differentiable? And where? That's a conjugate. Can you tell me? Take a minute. Is just simple conjugation a differentiable operation? And you just crank out the Cauchy-Riemann version. So write that as x plus iy. Break it into its u and v form. what are u and v here in terms of x and y, and then you can answer that question with great ease. I'm almost out of juice in my iPad, so we'll have to call it early today. I think we might call it, or if you want, you can hang out and start on the homework after we finish this, or I think I see something else in Lou's face, like wanting to leave maybe. I thought I saw a subtle smile there, like, no. What is this in UV? How do I rewrite this? What was that on the wind?
She said X
I
minus
thought
Y.
that's what she said, yes.
What did we talk about?
You're like Levita's life coach here, or like speech coach.
I hear everything she says,
I-
but nobody else does because she just doesn't say it.
And it's always right.
It is.
It's always right.
It is.
Okay, so u is equal to x and v is equal to what? Negative y. So let's do the Cauchy-Riemann check. So ux is 1, vy is, I don't need to go any further. Ux is not equal to vy anywhere. Conjugation is not differentiable. Oh wait, it's differentiable, nope, it's differentiable nowhere. Now, it is differentiable nowhere. It is a, think about what conjugation does. What does it do to the plane? It flips it, right? You take the z, conjugation turns that z completely upside down. This is not a smooth motion.
No, sure wasn't.
It wasn't meant to be. Didn't sound smooth. And it's certainly it's not just a simple rotation of the neighborhood around here. It's not just a simple scaling and rotation. It's like freaking picking it up and throwing it somewhere. Upside down. Let's do one more. Yeah, let's do one more. What do I got here? I wrote a few out before class. I was looking at a slightly different book. Yeah, let's end with this. This will be great. Kind of way to pull things together. Simple, elegant problem. And then we'll call it. Find real A and B, so A and B are real numbers, such that f of z equals 3x minus y plus 5 plus I times ax plus by minus 3 is entire. So I put it all together. Is entire. Find the constants A and B. Maybe there's infinitely many. Who knows? Kind of doubt it. What would you put? You're trying to make a problem for an exam and you want it to be entire. Enough juice to finish this. Maybe. It looks like you got it wrapped up. No?
Yeah.
Yes, I thought so. I thought I've learned your body language, yeah. Yeah, that's nice. Yeah. Is this looking okay? Just you can get a sanity check up here if you need it. Did you say something, Nate? That's okay.
That, partial Y,
Yes, sir.
isn't that B?
Oh, shit, thanks. Yep, good call, man. Good call. Yep, got a little crazy there. Yes, sir. Yeah, thank you. So you totally have this mastered. Good work. I love being corrected in a math class. Pretty much hate it everywhere else in life. So we need ux to equal vy, so b has to be 3. These two have to be opposite each other, so a has to equal 1. And now we have an entire function. So let's see, I gotta put them back up here, so let's see, so that's 3y there, and then 1 there. There's a symmetry, but it's not obvious unless you know Cauchy Riemann. Yay! Thank you, friends. So, how about that homework I gave you? Let's see if we can shoot for next Wednesday.